Okay. First off, many thanks to the organizers for inviting me here. This is actually my first time in Bonn, and I've certainly both enjoyed the conference very much as well as just walking around the city. I wouldn't mind being invited back sometime. Okay, so today's talk is going to concentrate on countable model theory. In other words, all languages are always going to be countable, but we're going to be looking at the class, so given a theory, complete or incomplete, we're going to be concentrating on its class of countable models, and just trying to get dividing lines for the complexity. Now this in some sense might parallel what Shala did, again looking at countable theories, where he looked at classes of the number of uncountable models, etc., and had this whole hierarchy, and from that various things, stability, superstability, a million adjectives came out. However, we're going to see that almost all of those are worthless. We're going to need brand new dividing lines. To sort of see this, it's well known that, let's put this back, that DLO, dense linear order, and the random graph are both Aleph zero categorical, as simple as possible, yet they're unstable. Conversely, and perhaps oddly, if you want to think about, say, some of the best behaved things, there's an uncountably categorical theory with the property that it has a reduct, which is Borel complete, which is as complicated as possible. Now in the reduct, say omega stability will be preserved, but yet chaos can ensue. I'll define Borel complete later, but think of it as complicated as possible. Okay, and this is a status report, which indicates that there's still a lot to do. And say about 10 years ago, I would say things looked pretty good. It seemed like we had a pretty good understanding of things. But in the last 10 years, things have gotten precipitously worse. And this isn't because of any errors or corrections of things. It's just there are more examples. The world is broader than one might imagine. So the point of today's talk is to try to indicate that to you. So there will be many, many open questions, and I'm eager to have people talk with me or just completely solve them on your own. And today we're going to be focusing on Borel reducibility, but Turbo was mentioning that there are many, many different reducibilities, say in like effective reducibility, and I'm going to be giving many examples, and it might be of interest for people working in effective reducibility to say, how do you analyze these examples? Okay, so with that all as a preamble, let's get going. Turbo mentioned this briefly. There we go. So again, all languages will always be countable, and then we can look at all L structures with universe omega, or the natural numbers. And to this, we can put on a topology. Actually, there are some choices of the topology, but here, so we take a base for it for any formula and for any finite tuple of natural numbers. We look at the models for which, with universe omega, for which this holds. And for what I'm going to do, it's going to be so crude, we only care what the Borel subsets of this are. So whether or not I take all atomic formulas or quantifier-free formulas or formulas with quantifiers, the topologies will change, but the Borel subsets will not. So it really doesn't matter. So obviously, S infinity, the group of permutations of omega, acts on these as homeomorphisms. That just given an L structure M, then we can talk about sigma of M, just permute its components, and since it's preserving all formulas, that will be an isomorphism. Okay, great. And for a theory if you just write down what it is, a theory T or possibly a sentence of L omega 1 omega, the collection of its models will always be a Borel subset of this, and moreover, it will be invariant under this action that I gave, simply because just M and sigma of M will be isomorphism with sigma. Sigma is the isomorphism between the two structures. Then, and it's a old theorem from 1960s of Ken Lopez Escobar that the only Borel and invariant subspaces of structures are the models of phi for some sentence phi in L omega 1 omega. Now, oops. Nope, not quite in time. So we're going to be concentrating on first order theories, but for the theory and a lot of things, it's sometimes is nice to slip into L omega 1 omega, sentences of L omega 1 omega. And in fact, for getting information about a particular theory, there might be an associated phi that will be relevant. So from time to time, we'll do that. Okay. Great. So we want to study the complexity of the class of models of T modulo isomorphism, or more generally, the sentence of L omega 1 omega. And Friedman and Stanley proposed this notion of Borel reducibility. So we have a class T1 and T and S theories in different countable languages. And we want to say that models of T are Borel reducible to S, just if there is a Borel function in the sense defined, which preserves isomorphism in both directions. So this is certainly what Turbo was mentioning. And there is a maximal class here, so we call T Borel complete if it's as bad as possible. In other words, if every theory Borel embeds into T for every S. So examples include graphs, abelian groups, fields, linear orders, and as just note, if you weaken the theory, you enlarge the class of models, making it easier to be Borel complete. Turbo mentioned this, but saying as an example, in the case with fields, this was stated in the original Friedman-Stanley. There was actually a problem with the proof, but then much, much later, Dave Sahota, a student of David Marker, proved that the real closed fields are Borel complete. And hence, all fields are, and we can recover this. Okay, great. Seems to only work if I go this way. Now, just the lay of the land, what's sort of a picture of things? Well, for any theory T, let's look at the equivalence relation of isomorphism. That's always Borel, that's always an analytic thing. Just if you write out M is isomorphic to N, just if there is an F such that blah, blah, blah. But sometimes it's Borel. And from the talk a couple days ago, David told us exactly when that is. So for a specific theory T, isomorphism on T is Borel if and only if you look at all of the Scott ranks of the countable models, that's uniformly bounded somewhere below omega 1. You don't want it to allow this. And this is simply because if you have this uniform bound, then isomorphism will be equivalent to alpha star back and forth equivalence, which is easily seen to be Borel. Okay, good. And why this matters is that the original work of Friedman-Stanley, but then most notably Hjorth, Kekris, and Louveau, gave a really detailed analysis of the possible Borel cardinalities that can occur when isomorphism is Borel. And this is simply because becomes an example of a Borel equivalence relation, and Kekris has literally written books on the subject, so a lot is known. So then from this, we can get a picture of what's going on. So roughly, the picture is we have this top class of being Borel complete. And you can easily see that, say, graphs are in here, and there are graphs of arbitrarily large Scott height. So none of these, so here isomorphism T is not Borel anywhere here. But then there are the Borel guys. And among this, try to keep it here, we have a benchmark. So starting with T0, which is the theory of, say, any thing with countably many countable models. And then to that, the next level of that, or another level, is T1, which is what's called the Friedman-Stanley jump of this. So we just add an equivalence relation, assert it has infinitely many classes, and say that each element of this, maybe I can just draw a picture here. So these are all going to be models of T0 throughout. Then that's a larger thing. So if integers characterize T0, then the reals will characterize being in T1. And then we can continue this process. T2 will be the jump of T1. And this corresponds to countable sets of reals. T3 dot dot dot, we get T alpha dot dot dot. And there are various comments you can make that, first of all, so everywhere in this picture, isomorphism T is Borel under this cone. Whoops. Should come back soon. You can easily see that this is downward closed. So in other words, if something is Borel and something else is Borel reducible to it, then isomorphism down here will be Borel. But moreover, this sequence, this internal sequence is cofinal in here. If you give me any S for which isomorphism S is Borel, it will be below at least one of these, and hence others. And we'll get back to this, but at some point, in the Friedman-Stanley setting, these are strictly stronger in terms of Borel reducibility. And what Hjorth, Kekris, and Laveau, they sort of filled in many of the possibilities here. These are benchmarks, but there are many classes inside here. But things are pretty well behaved in this part of things. Great. So I think I've said all of this. So then there are some definite success stories. Remember, what we're trying to do is analyze the classes of countable models of some theories, and there might be various possibilities. So Richard Rast proved that among colored linear orders, it breaks into three possibilities. Either the isomorphism is less than or equal to T1, and that goes by the name in Borel complexity of being smooth. So in particular, all of isomorphism will be Borel there. Or it's equivalent to T2 somewhere higher up. Or if it's neither of those, then it's Borel complete. So this is nice, and you can characterize exactly which colored linear orders have each thing. Then similarly, Rast and Sahota did the same with any complete O-minimal theory. And it proved, curiously, it's the same three things. Either it's smooth, or it's Borel equivalent to T2, or it's Borel complete. I have some partial work with Shalad among omega stable theories that if they are bad in either way, of either having ENI DOP or ENI deep, then T is Borel complete. But to give a full picture of what happens with omega stable is, well, it seemed more optimistic 10 years ago than it does now. So that's a partial answer. Then also more recently, Danielle and I proved that, so we're studying modules. So fix a countable commutative ring R and look at the incomplete theory of R modules, TR. And, I don't know if you can see this. It'll come back, it'll come back. So, I hope. There we go. So either there are only countably many models. Think if R is a field, then we get just, they're talking vector spaces, or it's Borel complete, and we can see exactly where it is. So, so taking the case when R equals Z, the integers, we get that the class of abelian groups is Borel complete, simply because there are uncountably many countable models. And the same is true with torsion-free. So that's kind of just as a special case of all of this. Okay.
Is that precisely the line field or not?
No, 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 no. You could have, no, but it's close. It's either uninteresting or else nearly a field, but it's, okay. Yeah?
I'm probably embarrassing myself, but can you tell us what the top deep?
At the coffee break, I would be happy to. It would take a while, and just think about them as being complicated. Okay. Okay, but something that was alluded to both in David's talk and Barbara's, there's this, if we pass to L omega 1 omega, we look at these abelian P groups. And those are described by Ullmann variants. And certainly, so the Scott heights are unbounded in omega 1, so isomorphism is non-Borel, but yet it's going to be somewhere out here, abelian P groups. But I actually wrote this a little bit too high if this is increasing strength, because you can prove that this T2, you cannot embed countable sets of reals into phi. And this is a precise way, David was saying that these guys are very thin going up. So this is a statement to that effect. So really this was too high. I should have it abelian groups, abelian P groups. But note that clearly, since this is non-Borel, so these guys are just incomparable. This guy cannot be below here, otherwise isomorphism would be Borel, and I'm asserting that it's not here. So these guys are just incomparable in Borel reducibility. Okay, continuing on. Whoops, onward. So, this was the state of affairs. I think this abelian P groups was even mentioned in the original Friedman-Stanley. But if we're just concentrating on theories, there's this wild conjecture you could make that for first order theories, that this is either your Borel complete or isomorphism is Borel, in which case things would be wonderful. Actually, a colleague made this conjecture. I will not name him. to not embarrass them, that every first order theory either has isomorphism Borel or is Borel complete. Simply there weren't any examples known. However, some evidence why this would be true, that note that this would imply Watt's conjecture. If the wild conjecture were true, simply because if you have a counterexample to Watt's conjecture, this was, again, David was mentioning, then isomorphism cannot be Borel. Just think that your Watt ordinal is omega 1, but yet, since there are fewer than continuum many models, you must be below, or T1 cannot embed into it. So, a counterexample to Watt's conjecture, if it existed, would be somewhere sort of even lower than this. I'm not saying, probably incomparable to this. Okay, so let's continue on. So what we'd like to do now is, so we had these success stories of colored linear orders or O-minimal theories or things where we have a lot of control. Let's go even more. So at first, we thought this project was going to be ridiculously easy. Let's think about weakly minimal trivial theories. So these are super stable rank 1, but let's take a really, really simple toy example of this, independent unary predicates. So we have UNs, just unary predicates, and the axiom state that all Boolean combinations are consistent. The canonical model of size continuum is that UN will hold if the nth bit is 1. So model theoretically, this is really, really boring. It's weakly minimal trivial. I coined a phrase mutually algebraic from different reasons. And it's also really boring in terms of Borel complexity. What does a countable model of this look like? Well, you're just going to be naming, you have a pool of continuum many colors, and you're just going to be picking countably many, and for each color, you're going to have either 1, 2, 3, or infinitely many different colors. So this is just countable sets of reals. What's the big point of this? Well, whoops, sorry. Let's look at a reduct of this. So a reduct, I'm going to use this term a few times, just means that every atomic symbol in the new language is zero definable in the old one. So, so we have the same 2 to the omega, but now on En, each En is just this conjunction of agreeing on the first n coordinates. Now, model theoretically, so you want to say what's the difference between IUP and binary splitting refining equivalence relations. So the name here is indicative of that. So there are 2 E0 classes, and then E1 splits each one of those into 2. So it's this binary splitting and refining. So now, the difference is model theoretically, IUP has continuum many 1 types, while REF bin simply has a unique 1 type, just x equals x. But there are continuum many strong types extending it. And the thesis we're going to be seeing is that this notion of Borel reducibility behaves very poorly with respect to having a perfect set of strong types. That isn't the only obstruction, but it will be considerable. So a theorem of the 3 of us, Ulrich, Richard, and myself, is that this REF bin, this reduct of something very easily understood, is not Borel complete, but yet isomorphism is not Borel. So this was the first known example of this. and it defeats the wild, unlikely conjecture. I mentioned, too, only in passing, that by very similar methods to what I'm going to show for one, Martin Kerveen had an example of an omega stable theory of depth 2, but that also has a very similar phenomenon to that. So this is part of the reason why, in my work with Shala, things have stalled out a bit, that life at depth 2 is quite involved. Okay, so we're going to concentrate on one, and I'm going to say, showing that isomorphism is not Borel for REF bin, there's a self-similarity argument that if we're just looking at equivalence classes like this, the idea is that if we just delete the first guy, we really get up to shifting the ENs by 1, we get 2 copies, each of which are just like REF bin, and we can manipulate among those. So thus, there cannot be a uniform bound on the Scott heights. But what I really want to emphasize here is, how do we show that things are not Borel complete? Now, showing something is Borel complete is very analogous to like NP completeness. There's this huge pool of things, so you pick your favorite one and you embed it in, done, you're happy. But it's much harder to say that you do not have a Borel reduction into it. You need some sort of other method. And crucially, if we take my word for it that isomorphism is not Borel, it's not living in here, and worse, all of Kekris's wonderful theory of Borel equivalence relations is going to be thrown out the window. We need some brand new ideas for this. And it isn't simply because, you might be tempted to say, well, IUP is so simple that there can't be any other reduct which is Borel complete. That we'll see actually is false, that there are other ones. Great. So for that, what's our new tool? Well, let's go back to something which we've now seen many times, Scott's theorem, that every countable M has a canonical Scott sentence, phi M. I'm adding the word canonical because I really want to have a mapping, a unique mapping going from M to its Scott sentence. Typically, there can be literally many Scott sentences, but they're all equivalent to each other, so I'm picking one particular one. But we're saying that for any countable model, N will be a model of the Scott sentence if and only if they're isomorphic. Great. Now, Salma asked a question earlier that we can really look at models of any size. So curiously here, we're going to be analyzing, getting information about the class of countable models by looking at uncountable models of this. So Barwise and Nadel, the same Mark Nadel mentioned this morning, that every structure you can think of is potentially countable. You can always do something drastic and take a forcing extension of the universe in which you collapse card M plus down to Aleph 1, and then, by golly, it's countable. Okay, and similarly, for any 2 structures, you can collapse them down. There's a forcing V of, so that in V of G, both M and N are countable. And now we note for countable structures, being isomorphic is exactly the same as being back and forth equivalent. Now, isomorphism is not preserved under forcing extensions, but back and forth equivalence is. It's the same as that satisfiability is preserved. So, as a result of that, we can look at any structure of size M, say of size kappa. It has a canonical Scott sentence, much the same way, so that for any N, N will be a model of its canonical Scott sentence if and only if they are back and forth equivalent. Okay, so just everything goes through nicely if you rub out isomorphism and put in back and forth equivalence, but that's preserved. Okay, and just as notation, we wanted it to be a unique object. So now here, L infinity omega is, well, L omega 1 omega, we allowed countable disjunctions and conjunctions. Here we're going to allow disjunctions and conjunctions of arbitrary size, but again, the omega at the end, any formula can only have finitely many free variables. Okay, great. So then there are two things to think about. Well, okay, so let T be any theory, then it has models arbitrarily large, but we can look at its canonical Scott sentences, the family of those, and we can count those. That's going to be the number of models of T up to back and forth equivalence. Okay, so that's a measure in some sense of the complexity, not that will relate back to countable models, and fact that if a theory T is weakly minimal, then it has the wonderful property that if you take a model N, no matter how large, then it has a elementary substructure of size continuum that's back and forth equivalent to it. So thus, we have an absolute bound on the number of models back and forth equivalent. It's going to be simply 2 to the continuum, in other words, Beth 2 possible models. Okay, so in terms of this, the abelian P groups have CSS, the SAT, so these are guys that are satisfiable, is a proper class. That, as Salma was suggesting, that we can run the Ulm analysis now not with countable, but just of any arbitrary length. So we get that that's a proper class, but still, just looking at the countable model, it's still very, very thin. T2 does not embed into it. Now, among the Borel complete guys, curiously, sometimes we're going to have only countable, sometimes we'll have a proper class of this CSS SAT will be a proper class, but other times it won't. This is some indication that this isn't quite the right notion. So we need to go one step deeper with this. So here you might want a bit of coffee, but so a potential canonical Scott sentence for T is going to be some psi, which is in L infinity omega, say L kappa plus omega, such that when you do a forcing just of this, this canonical Scott sentence to make it in L omega 1 omega, then it becomes a Scott sentence. So in other words, that there is some countable model M whose CSS is the original psi. But curiously, this can occur even if in the original universe V there were no models of it. So this is perhaps, I want some disbelief, but here, just in terms of an example.
Is it possible to say quickly what the forcing extent, what is a forcing?
It'll simply be just collapse, what is it, kappa plus to aleph 1. Now,
I want to know the definition.
oh,
Maybe it's too much. Is it possible to get the definition in a minute? Or?
this is straightforward, isn't it? You just take, no, sorry. So this goes by the name of Lévy collapse. So you can collapse any cardinal down to a smaller uncountable any uncountable cardinal down to a smaller one. You just take approximations of size of size. So we would just be taking all countable subsets of M. Okay. I'll answer that more fully. Okay, great. So just as an example of this, first of all, you can characterize any particular ordinal by a sentence in this L infinity omega, and you just prove this straight out by induction on gamma. If you have it uniquely for gamma, then gamma plus 1, etc., and at limits you just take the conjunction of things. And something a little deeper is that you can have a complete sentence of L omega 1 omega, which means that up to isomorphism there's only one countable model that homogeneously characterizes aleph 1. In other words, that there are models up to size aleph 1 and no more, but there also is a pot. There is a unary predicate U, and inside that you just have an infinite, totally indiscernible set. And this is wonderful, which means that you can code when you have such a thing. So we can merge these together. Then let phi star be phi, but then we now insist that we add a less than to the order, to the language, and we insist that we have a linear order on that. Then, since there's this absolute bound of the cardinality of models of phi, CSS sat is just bounded by 2 to the aleph 1, but really corresponding to every ordinal gamma, for every ordinal gamma, we can collapse that in, so we get many different potential canonical Scott sentences, one for each ordinal gamma. Okay, and it turns out that this is rather the magic bullet. So what you want to do, just given a good old countable theory T, we want to count the number of potential canonical Scott sentences of this. And arguably, amazingly, this gives a method of showing that S is not Borel reducible to T simply by counting. Remember, Borel cardinality was intended as being, just acting like a cardinality. Here we're taking it literally. We're associating a cardinal to it. And if there is a cardinal gap, then we have that we're not Borel reducible. And so then, clearly, now if T is Borel complete, then this cardinal will be this double braces T will be a proper class, even though CSS sat might be a cardinal. So this widening thing is where the theorem really occurs. But on the Borel side, we can bound this quite nicely, that this Borel, the number of potential canonical Scott sentences is bounded at Beth omega 1. And a big open question is it possible to have a theory which is a cardinal bigger here? So in a moment, we're going to see that off to the side, rather than just spotted things, we're going to see that there's a whole bunch of things. But what still remains open is there something strictly between these which is above all of these, as it would need to be. Okay, good. So here just a comic aside, that if we have any theory, then I defined the Friedman-Stanley jump is just add an equivalence relation and put copies of the theory in each one. And Friedman and Stanley proved that isomorphism is, that if isomorphism is Borel, then very proudly he used Borel determinacy to show that, that there was no Borel embedding from T prime into T. The fact that T embeds in is easy. But for us, we now have essentially a one-line proof of this, that if T is a cardinal, and which follows from isomorphism being Borel, then it's easy to just count the number of potential canonical Scott sentences of T prime is just 2 to the cardinality of T. So then the corollary is that T is strictly below T prime simply by Cantor's theorem. Just literally we're saying that 2 to the T is strictly larger than T. Okay, that was an aside. Now, for those of you who are unhappy with this notion about the difference between these canonical Scott sentences that are satisfied in V and the potential canonical Scott sentences, for some theories T, they're the same. And this has been occupying a huge amount of my time and energy. I can say that sometimes the answer is yes, sometimes no. Even among the Borel complete guys, sometimes some theories are grounded, others aren't. I really don't understand what's happening here, but some negative examples are that the class of linear orders is not grounded, and the class of abelian groups is not grounded. But some nice results are that these benchmarks, these T alphas, are all grounded. And if you're grounded, then it's much easier to be able to count the number of models. So we get that. And the key to why REF bin is so nice is that if you look at the incomplete theory of refining equivalence relations, so if you simply say that E1 refines E0, E2 refines E1, ... without specifying the number of classes or anything like that, all of those will be grounded. For those of you who might know, this groundedness is a slight strengthening of something that Zapletal came up with about pinned equivalence relations. And they have a paper saying that the incomplete theory of acyclic graphs is pinned, but in the same proof gives that it's grounded. Okay, now, once we know that REF bin is grounded, we're on easy street, because we're saying that this CSS potential is equal to CSS of the satisfiable ones, and because it's weakly minimal trivial, or just weakly minimal, that second cardinality is just Beth 2. And what that's saying is that T3 cannot Borel embed into here. So REF bin is slightly up from this, but it would still be below the T3. Okay, and as I indicated, life is going to get worse from this. I know, looking at your faces, I'll try not to make it worse for you, but it's going to be worse for me. Let's continue on. So back to maybe easier streets. So this independent unary predicates. We had this thing. So we can develop many, many different reducts. And so for all of these, they're going to have exactly one type, x equals x, but they're going to have different behaviors of the strong types, different linkages going on. Refining is just one thing we could have. A second in some sense, orthogonal thing is we could have cross-cutting equivalence relations where every En has two classes and they're independent of each other. So in other words, if you have finitely many ENs, then to say that the conjunction will be an equivalence relation with 2 to the power of f possible classes. So they're just independent. So in this thing, with two splitting, things are almost like IUP. Think about if we have these equivalence relations that are independent. If you name a point, then you can now, you've changed every one of the ENs really into a unary predicate. You could either be EN, every other point is either EN equivalent to that or not EN equivalent to it. So it really becomes IUP after naming a point. So isomorphism is Borel, hence grounded, hence, and then we get the bound of Beth 2 for its cardinality, but again, that's comparatively boring. Now, let's change 2 to 3. So cross-cutting, but now each En has 3 classes and cross-cut. It's easy to see that this still is a reduct, and from some rather complicated arguments I'm not going to give, here isomorphism is not Borel, but it still has potential cardinality Beth 2, which is so it's very far from being Borel complete. It's roughly at the level of REF bin, but it's open as to whether or not this guy is grounded. So in order to establish these other things, we're going to need some other techniques. So then another example, if we just, is that if we suppose we have cross-cutting where each En has n classes. So you can get this by clumping together various things. And they're independent or they cross-cut. Then CCID is not grounded, and it is Borel complete. So the number of satisfiable guys is still Beth 2, but the CSS potential has become a proper class. So these are wildly different things, and then it's a little bit too difficult to explain, but still another reduct of this IUP, which is going to be some entangling of equivalence relations, all of which have finitely many classes. We get this theory EQ star. In it, isomorphism is not Borel, it's not grounded, so I don't have any of the normal tools. But if you give me a large cardinal, in other words, an omega Erdős, so not that large, then we can prove that it is not Borel complete. Now at this point, this should seem sort of backwards. Again, this conference is all about definability. I thought that somehow Borel reducibility fit into definability because things are supposed to be definable. But in that realm, you would expect that things should be absolute. It shouldn't depend on whether there's a large cardinal. And you might be saying, oh, but what about Schoenfield absoluteness? We're really just talking about countable models, so this should apply. But if you carefully go through the count, it's sort of one level too high for Schoenfield absoluteness to apply. So again, we do not know that the large cardinal is necessary, but the only existing proof that we have has this. Okay, so why am I torturing you with all of these toy examples? IUP, we started, was boring, and now I'm talking about various things which are complicated with that. Oh, okay. I'll get to that in a sec. But if you want to understand how we could have all of these wild behaviors going on, it's all on the behavior of the strong types. And if you want to be measuring that, what really is going on is there's a profinite group of just elementary permutations of algebraic closure of the empty set that just are describing the maps of the allowable permutations of strong types. And in IUP, there are no strong types. Everything is just a type, so the group is rigid. With this thing about naming a point, the corresponding group is 2 to the omega with plus, which is abelian, and just in general, abelian group actions tend to be really boring things. They're all regular, and life is good. In CC3, sort of the reason we don't have that, but at least the group has bounded exponent, which turns out to be relevant. But in the CC, where we have sort of infinite or arbitrarily large En classes, the G is complicated. In particular, G has elements of infinite order, which is going to allow for the coding. So again,
You write 2 to the omega here, does that mean a countable direct product of copies of?
yeah, so if you want, it's just the group, just product of 2 with plus coordinate-wise.
But does 2 mean Z mod 2Z?
Yeah,
Okay. Yeah, okay.
sorry, yes, okay. You can tell I'm not a group theorist. Okay. But then I want to say that all of this chaotic behavior, sort of the point of showing all of this, is that that if we take any theory which has continuum many one types, then just scratch your head, you'll see that IUP is a reduct of such a theory. That, again, just by Cantor-Bendixson analysis, if S1 is uncountable, then we have this perfect set given by zero definable formulas. And you just say if we're going to go left at a branch, we call that UN holding. If we're going to go right, it's UN failing, etc. So we get a reduct of this. So all of these behaviors occur sort of almost everywhere. Unless any time we have continuum many one types, then we get all of this behavior. So as a corollary, all of these behaviors in any such theory, some reduct of it will be Borel complete. Others will not be Borel complete, but be non-Borel. So in other words, in this region here. And for others, we might even need a large cardinal to answer whether or not it is Borel complete. Whew. Okay, so just again, on a different note, so with this, we'd like to dive in, and so groundedness is too much to hope for. We'd like to somehow be separating the good from the bad with this. So sort of a brand new definition. So let's say a structure M admits nested sequences if there's an infinite sequence AN which is sort of weakly indiscernible in a sense that, in other words, the type of AN and AM, the quantifier-free type of AN and AM are the same over all of the predecessors of AN. So think about this as being a very, very weak notion of being indiscernible. And a sentence of L omega 1 omega forbids these if no M allows something like this. This turns out to be a very tight restriction, and if a countable model M forbids nested sequences, then its automorphism group is highly constrained. It's CLI. I'm not going to go there, but it's a tight restriction, and then without anything about groundedness, we can just prove that if phi forbids nested sequences, then they're at most Beth2 potential canonical Scott sentences of it. Why? Now we want to say, wait a minute, why? We're talking about theories, right? So in a theory, if a theory admits an infinite model, it has an infinite indiscernible sequence. It has a model with an infinite indiscernible sequence, and that would certainly admit nested sequences. What's the point? Well, say in our weakly minimal, guys, these indiscernible sequences that we come up with are rather boring. That there really is this type E infinity. It's not first order definable, but it's definable in all of the ENs, and just being the conjunction of all of these. And any infinite set of realizations is just totally indiscernible, but somehow that isn't giving us any information anyway. So we want to blot this out. So let psi, applying this to this cross-cutting equivalence relations with 3, so it's the first order theory, CC3, together with one infinitary thing, saying that you don't repeat, that every E infinity class has at most has one element. Then, then in this, we're going to say that the psi CC3, that forbids nested sequences. That's sort of the way in which we're getting this bound of Beth2. And then it's easy to just see by transfer back to the first order case that if we know that just the only other models would be multiplicities of this, so we still get this Beth2 bound. And, right, so in some sense, this thing about forbidding nested sequences is in some way of coding that the group G of elementary permutations has bounded exponent. So it's a way of doing it. So thus we get this bound that T3 does not Borel embed in it by this roundabout method of passing to this infinitary sentence, saying that this has a very, very tight constraint on it. That will bound the number of models of it, and then rolling it back to get this non-Borel reducibility. With that, thank you for listening, and